Yes, it's okay.
Nguyen, right?
Yes.
And you will talk about the average covering.
Just so thanks for the invitation, and thanks everybody for coming here. And I'm Tùng Nguyễn from KAIST, I'm still an undergraduate student. And I hope my talk today will be kind of my thesis defense because I'm going to graduate this summer, hopefully. Yes. So this talk will be about the average cut-rank graphs, cut-rank-based parameter that myself with Professor Sang-il Oum have been investigating since 2018. And I still remember when I first tried to get used to the cut-rank function and vertex-minors. It was really tough, and I tried to play with the cut-rank function, and somehow I found out this parameter. So let me just move on to. So the content of this talk will be, you consider 5 parts. The first one will be background. But this background will be a bit kind of long because there are kind of many necessary notions to come up with the results related to the average cut rank. And the second part will be the main parameter of this talk, the average cut rank. And the third part will be the main results. And the fourth part will be the proof of the fact that the maximum cut rank is bounded from above by 4 times the average cut rank. And it seems that people are somehow interested in this bound. I have no idea why. And the last part, if I have time, then I will present other results related to the parameter. Okay, so let's go to the background. And so we know that, so I guess everybody here already knows that two distant vertices in a graph G are twins if they have the same neighbors other than themselves. But the thing about that definition is that we require x and y to be distant. So, but to make them to be a relation that forms an equivalence relation, then we need them to be equal. Okay, so we define two vertices. We say that two vertices x and y are twin equivalent if either they are the same or they are twins. And it is a trivial fact that this relation is an equivalence relation on the vertex set of G. And every twin class is either a clique or a stable set, right? So it's just kind of an easy fact. And the neighborhood diversity of G is just simply the number of the equivalence classes with this twin equivalence relation. So this is the number of twin classes of G. And this notion was introduced by Lampis in 2012, but was actually investigated earlier by Tùng and Koloff in 2006, but under a different form. And this parameter will play an important role in the results related to the average cut rank. Okay. And so now I'll go to local complementations and vertex-minors. So the local complementation at a vertex V in a graph G is just an operation switching the adjacencies between the neighbors of V. And the resulting graph is denoted by G star V. And it is trivial that if you locally complement a vertex twice, then we get the original graph. Okay, so for example, you can see here, sorry, the numbers are a bit small, but I guess it's fine. The vertex 1 here, if I locally complement 1, then I will change the adjacencies of the vertices 2, 3, and 5, as you can see here. Yes. And two graphs are locally equivalent if one can be obtained from the other by a series of local complementations. Okay, and we say H is a vertex-minor of G if H is an induced subgraph of a graph locally equivalent to G. And actually, you can say in another way that H is a vertex-minor G if H can be obtained from G by a series of local complementations and vertex deletions. Okay, and it's also trivial that if H is an induced graph of G, then H is a vertex-minor G. Just straight from definition. Oh, but I forgot to mention that in this talk we will consider graphs up to isomorphism. Okay, to avoid any confusion. Okay, so we come to the cut-rank function, and so for this drawing HY in the vertex set of G, we let we just denote this rho G star be the rank of the cut, the XY cut in G. So here AG is the sorry, it's a bit oh no. Okay, AG is the adjacency matrix of G, and here I denote AGXY the submatrix of AG, where the rows are indexed by X and the columns are indexed by Y. And this matrix will be over the binary field. Okay, so simple. And the cut-rank function of G is the function rho G from this from the family of subset of G to the integers, which is defined by this way. So it's actually the rank of the cut from S to G minus S. Okay, and a trivial fact is that this function is symmetric, right? Straight from definition. Not really, but anyways. And kind of fundamental result by Boucher says that no matter how you locally complement a vertex in a graph, then the cut-rank function is preserved. So it means that the cut-rank function is preserved by local complementations. And we have some cut-rank based parameters which are not increasing by taking vertex-minors. So we have rank width, we have linear rank width, and rank depth, but I'm not sure if these are all. I mean, at the moment, I think, and rank depth is actually a bit new, as far as I know. Okay. And now we come to quasi-ordering. So a quasi-order for set X and a binary relation is, I mean, it will satisfy the reflexivity and the transitivity. So if we add the symmetry, then we'll get a partial order. But here we don't have symmetry, so we only have a quasi-order. Okay, and X is well quasi-ordered by this relation. If for every infinite sequence, you can always find two distant elements that are actually comparable. Okay. Yes, so
I think I is less than J, probably.
Yes, I think just there is a mistake. So if you have any questions, then just interrupt me. Okay, so so this theorem is well known. But in this one, I will not mention what a graph minor is, but I will state this as because I believe that it is a big source of motivation for vertex-minors theory, and it's just a very well-known theorem of Robertson and Seymour, saying that the class of all graphs are well quasi-ordered by graph minors. And a conjecture by is that the class of all graphs are well quasi-ordered by vertex-minors. And as far as I know, this conjecture is still open. And to illustrate this conjecture, he proved that the class of graphs of finite rank width is well quasi-ordered by vertex-minors. And in this talk, when I mention a class of graphs, that class will be closed under induced graphs. Okay, just to make sure that there's no confusion. And for well quasi-ordering with respect to induced graphs, there are two results. The first result is by Ding in 1992, saying that a class of graphs of bounded rank depth is well quasi-ordered by induced-subgraphs. Actually, but 3 depth and rank depth, because actually he proved it in a more general sense. He proved that a class of graphs without a long path as an induced-subgraph is well quasi-ordered by induced-subgraphs, but the rank depth of a path, of a long path, is big. So this result is implied.
But when he says the long path, it was probably by subgraphs. So
as far as I remember, what he proved is that the class of graphs not containing a long path as an induced-subgraphs.
Okay, so we can.
Yes, we can deduce this result.
Yes.
Okay, and the second theorem is by Tùng and Koloff in 2006. It states that a class of graphs with bounded neighborhood diversity is well quasi-ordered by induced-subgraphs. But we'll see later that the second result is just a corollary of the first result. Okay, so I'm not sure if the next slide will be included in the background, but I think that this will be somehow helpful to some people here, because it's just kind of basic thing. So we just note that the twin classes are not preserved under local complementations. So for example, so let's say this is a big click, say Kn, or L large, and here is a vertex V. And if you locally complement V, then what you get is a star. Right. So initially, this has only one equivalence class, no, only one twin class. Which is so ND of this is 1. But here you have ND. It's true because V here and this guy here from 2 twin classes. So, and this is a little bit annoying, especially if you consider a more general case. That is, so let's say if Kn is included in the bigger graph, and let's say these are twin classes. So twin classes. Okay. And if you locally complement V, then the type of these twin classes are still preserved somehow. So what I mean by preserved is that the clicks return into the stable set, and the stable set return into clicks. Okay. But now only V is adjacent to the necessary twin classes. And so this is a bit annoying because we still have these guys who are the twin classes. But now this twin class initially now becomes 2 twin classes. So it is a bit annoying here. And if you just take a look closer at this class, then you will see it is indeed a kind of star-shaped structure, which means that every vertex of degree 1 inside here also has degree 1 inside the U graph. So let's say this is G. And if we take a vertex, say U here, and here's U, then U in the new graph is a vertex of degree 1. So basically, we have 3 forms. The first one is the cliques. The second one is the stable sets. And the last one is a kind of star structure. Right? And no matter how you locally complement the vertices in G, then you will always get one of these types of classes. If you start with the twin equivalence classes, right? So for this kind of star structures, I will call it an attached star. So an attached star in G is an induced subgraph isomorphic to a star whose non-centers have degree 1 in G. So because the twin classes are not preserved under local complementations, and it is natural to ask for an equivalence relation, generalizing the twin equivalence relation, and satisfying that every equivalence class respecting this equivalence relation is invariant under local complementations. And it is a natural question, right? But and somehow we can do it. Yes. So we define this equivalence relation by the cut rank inequalities. And this looks a little bit artificial, but then we can easily deduce that the cut rank of x is equal to the cut rank of y, and it is at least cut rank of xy if only if either x is equal to y, or xy are twins, or one of them is the unique table of the other in G. So let's say if x is the unique table of y in G, then it means that y has degree 1, right? And we have a proposition here. And it says that this relation is indeed an equivalence relation on G. And every equivalence class is either a clique, a stable set, or it induces an attached star. And for this reason, I will call a star class to be an equivalence class in this equivalence relation, inducing an attached star. Okay, but just note that these 3 types are not entirely exclusive, because you may have classes with only one vertex. You may have the singletons, and especially for a clique and an attached star, you may have a component of size 2. And this can be considered as a clique and also an attached star at the same time. And now there's a question that somehow we need a submodularity proof for this proposition, especially with the first statement that this relation is an equivalence relation on BG. By submodularity, I mean the submodularity of the coupling function. But the thing is that our proof for this proposition is a bit ugly. It's a heavy case analysis, and it took us a lot of time to find a submodularity argument, but we failed. So if someone is interested, then maybe you can try to use the submodular property of the coupling function to prove the first statement. Because this condition is kind of neat and beautiful, but still. Okay, so so this is enough for the background. Any question? Okay, so now I'll go to the average cut rank. So it's just the expectation of the cut rank of X for uniformly chosen random subset X of VG. And formally, we can write this as this form. Okay, and so we have some examples here. So let me. So let's compute the average cut rank of K3, for example. By definition, it is and for every vertex set of size 1, we see that the cut rank is 1, so we have 3 times 1. And for every vertex set of size 2, we also have the rank 1, the cut rank 1, because of the vertex outside. Right? So, and this counts for 3 over 4. And similarly, you can compute the average cut rank of C4 and P4, just 9 over 8. And in general, we have that the average cut rank of the complete graph on K vertices is 1 minus due to the 1 minus K. And we can also compute the average cut rank of the complete power-type graph. And if you can check, so you can see here C4 is K32. And if you replace M and K by 2 here, then you will get exactly 9 over 8. And for the first statement, it is a bit easy, just kind of simple counting. But for the second, I'm not sure if it's really easy. But anyway. And to check this, you can let M equals 1, and you will get that they're actually equal. Because and this aligns well with the fact that the cut rank function is preserved by local complementations, right? And also the maximum cut rank of G is just simply the maximum over all the cut rank functions in G. And the maximum cut rank will play a role in this talk, so just remind it. Okay, and so now we come to the basic properties of the average cut rank. So the first is that if H is a vertex-minor of G, then the average cut rank of H is at most that of G, and that is easy. Why? Because if you see, then it is just really the inequality. Right, because all right, so that is easy. But this is kind of expected. And so now, to that, the rank width function, the linear rank width and the rank depth also have this property. But the thing is that if outside of H there is a vertex having degree at least 1 in G, then we get strict inequality. And this really boils down to when this inequality doesn't have equality. So it means that if there is a vertex of degree at least 1 outside of H, then there will be some S such that this inequality holds. Okay, and so just note this because I'm not sure if the other rank-based functions and parameters have this property. And another thing to note at is that the average rank is a rational function. It's a rational number. It's not an integer. So this inequality is somehow expected. And if G is a symmetric difference of two graphs, then we can somehow decompose G, the average rank of G, into two, and we get an inequality. Question?
What happens if G is a complete graph?
Is a complete graph? You mean the inequality?
Yeah.
Yeah. So you can return to right. So say if so let's say K and KL. K is smaller than L. Okay. Then we okay.
Oh yeah, I see. Yeah.
Okay. So if G is a symmetric difference of G1 and G2, then this inequality holds. Then the average rank of G is bounded from above by the sum of the average ranks of G1 and G2. And if you think about it, then it's just really the matrix inequality over the binary field. No, sorry. If, right? And in particular, if G decomposes into G1 and G2, then you still have this inequality. And if G is a disjoint union of two graphs, then the equality holds, right? And for corollary, we deduce that if you delete a vertex from G, then the average rank decreases by at most 1. And also the average rank doesn't increase. There is just a corollary of this inequality, and the fact that the average rank of the complete, the average rank of a star is at most 1. We just decompose the edges incident to V. Oh, sorry. Okay, and or what the rest statement hold for the maximum rank. So you can basically replace the average rank with the maximum rank in every statement, but not the red one. And a proposition by myself and Professor Oum says that if T is a star class in this equivalence relation, and V is in T such that the degree of V in G is 1, then we have this inequality. So let me explain a bit about this inequality. It is a good thing about the average rank because it aligns pretty well with that equivalence relation. So let's have a look at this bounded inequality. So it says that and here T is a star class. So T is actually U and B1 dk, for example. Here U is the center of the star with V1, V2, and here's Vk. And the rest here is G minus T. Okay? No, sorry, should be different. Okay. And as you can see, this G minus T is actually equal to right, because we are left with the isolated vertices if we delete U. So basically, we also have this inequality because it is equal to G minus U. Okay, so now you can see that if T is pretty large, then this inequality is pretty close. And if T is large, then also the right-hand side inequality is also close, because we already know that the average cut rank of G minus V is almost that of G. Okay. Any question? No. So let myself move on to the main results here. So is the first result, and if G has at least one edge, then the average cut rank of G is smaller than that of is smaller than the maximum cut rank of G, and it's almost the neighborhood diversity of G. And the main thing here are the two inequalities. This is the blue one and the red one over there. And the red one really means that the maximum cut rank of G is bounded from above by 4 times the average cut rank of G. And in reality, we have more results. So this looks a lot, but they are kind of simple and easy. And so we can put the minimum rank of G over the binary field in the first inequality. And in the second inequality, there is an appearance of CDG, which is a clique delta carbon number of G. So it is the least number of cliques that whose symmetric difference is G. Okay. But still, in this talk, I will only talk about the blue one and the red one. And so we have here some kind of big graph classes and with some parameters. And I will give the credit to Huy-Tung Nguyen and Sang-il Oum because I took this picture from their paper. So, but still, let's just forget those bounded classes for a moment and just concentrate on the blue ellipse. And inside here we have bounded neighborhood diversity. And in fact, by the previous theorem, we can replace the neighborhood diversity by a bunch of parameters like the average cut rank, the maximum cut rank, the mean rank of a finite field, and the clique delta carbon number. And somehow you can also replace neighborhood diversity by the number of equivalence classes respecting this equivalence relation. Okay, so we have a lot of things outside there. Okay, so now we come back to these two inequalities. And so come back to a result by Tùng and Koloff in 2006, saying that the class of graphs has bounded neighborhood diversity, then it is well quasi-ordered by induced-subgraphs. And in 2019, Gagnon, Hineni, Nessechu, and Obzalet, and Osuna Mendes, they show that the class of graphs of bounded neighborhood diversity has subgraph almost 1. And the class of graph of bounded subgraph is well quasi-ordered by induced-subgraphs, and this was also by Ding, 1922, right? Yes, okay. But so now you can see that the first result is actually implied by the second result, as I told earlier, right? And a corollary is that a class of graphs of part of average or maximum cut rank is quasi-ordered by induced-subgraphs, because the average cut rank and the maximum cut rank is tied to the neighborhood diversity, as illustrated in this diagram, this picture. All right, and so for every real alpha, for every positive alpha, there are only finitely many induced-subgraph-minimal graphs of average cut rank at least or larger than alpha. So we have to split this into two categories. The first one is at least, and the second is larger than, because right now the average cut rank is a rational number, and so we have to split the two. And alpha is a positive real number, so it's not only an integer. So it might be natural to ask for the size of the induced-subgraph-minimal graphs of average cut rank at least or larger than alpha. But that question is not so interesting if we replace the average cut rank with the maximum cut rank, because every induced-subgraph-minimal graph of maximum cut rank at least k must have size 2k. And to explain this, let me let's say G is an induced-subgraph-minimal graph of maximum cut rank at least k. So by definition, there is a subset S in VG such that the maximum the cut rank of S is exactly k, right? And this is equal to so now you can see there's S here. Now just think about matrix algebra when you're looking at this configuration, because this means that there will be a subset A of S and a subset B of Vg minus S whose cut has rank exactly k, and the size of A is equal to the size of B and k. Right? It's just matrix algebra. So let's say there's a matrix indexed by S with the rows and Vg minus S in the columns. And this has rank k. All right, and so there is a principal submatrix of size k times k, which has full rank, and this corresponds to the sets A and B. And so AB has size k, and the rank of the AB cut is k. So if you delete any vertex, say V, outside of A and B here, then the maximum cut rank doesn't change. So you can deduce that VG must be the disjoint union of A and B. And so G has size 2k, right? And a thing to note is that a vertex-minor minimal graph of average cut rank at least or larger than alpha is actually an induced-subgraph-minimal graph of average cut rank at least or larger than alpha, because such a graph must not contain any induced-subgraph of average cut rank at least or larger than alpha. Okay, and so to obtain the bound an upper bound on the number of vertex-minor-minimal graphs. We want to find an upper bound on the size of every vertex-minor-minimal graph. And by this method, in 2005, prove that a vertex-minor-minimal graph of rank quiz at least k must have size at least 6 to the k minus 1 over 5. And so we can deduce that the number of the vertex-minor-minimal graphs of rank quiz at least k is almost 2 to this number. Okay, maybe 2 to this number square because we count the edges. And so, but this question is still open for linear rank width and rank depth, as far as I know, right? Rank depth is kind of new, so maybe people haven't been investigating it. But for linear rank width, it has been open for a long time to find this upper bound. So now for induced-subgraph, we do the same thing. So to find an upper bound on the number of induced-subgraph-minimal graphs, we find upper bound on the size of every induced-subgraph-minimal graph. And so with following this idea, myself and Professor Oum proved that every induced-subgraph-minimal graph of average cut rank at least or larger than alpha must have size smaller than some function here. So here is the ceiling function. The sub is the ceiling function, and inside the brackets is the fractional part of alpha, because alpha is a real number. And this x is a sequence. And this sequence is defined by these rules. So this looks a bit intimidating. I hope no, but somehow it looks a bit intimidating. And but it seems not, because when epsilon is rational, then this sequence behaves as an exponential function, where the exponential term is quadratic. And the constant term inside here is universal. It means that it is independent of n and epsilon. But when epsilon is irrational, then maybe it really is intimidating. And this comes from the equidistribution property of the sequence. So there is a result saying that for almost every epsilon in 0 to 1, this sequence is equidistributed. So in this case, for me, it is kind of difficult to obtain a bound on the sequence because of this fractional part. Okay. And so you may note that there are two parts in the definition of the sequence. The first one is the purple color, and the second one has the violet color. And that purple color uses the bound that I mentioned earlier. And I put the purple color here because purple is just like a combination of blue and red. So you can see the neighbor diversity is almost this number of the average cut rank. And as you can see, there is a number 8 here and a number 8 here. Okay. And the second comes from the bound that I also told you earlier. That is the purple bound with the T, where T is a star class in this equivalence relation. Okay. Then this explains why we have 1 minus something here, because we have 1 minus something here. Okay. And so for the lower bound, a lower bound on the number of non-isomorphic induced subgraph minimal graphs can be deduced from that on the number of locally non-equivalent vertex-minor minimal graphs, right? Because we have known that a vertex-minor minimal graph is an induced subgraph minimal graph. And to obtain a lower bound on the number of locally non-equivalent vertex-minor minimal graphs of linear rank width at most k, Nguyen and Oum in 2014 deduce this number as an attempt to get some information about the size of the list of vertex-minor-minimal graphs of the rank width at least k. And so again, as far as I know, this is still open for rank width and rank depth. Right? Maybe people don't care about rank width and rank depth. I mean the lower bound still. And myself and Professor Oum in 2020 found that there are at least this function of locally non-equivalent vertex-minor-minimal graphs of average cut rank, at least alpha. And I put alpha plus 1 here because alpha might be in 0 to 1. But actually, the term in the exponential function is really superlinear. And so you can treat this as something like alpha to the alpha, maybe alpha to the C alpha, where C is a constant. And one thing to note is that the constant inside here is also universal. It is entirely independent of alpha. Okay, and the graphs in the construction are forest. So to do this, we constructed a series of graphs which are forest and have large average cut rank. And we used a result of Boucher in 1988, saying that if two forests are locally equivalent, then they are isomorphic. And the bounds that I mentioned earlier, where T is a star class and this bound. Okay. This is somehow expected because we can always find at least two star classes in a forest, right? Because there are always at least two vertices of degree 1, well, which don't have a neighbor in common. Okay, so now I have maybe 10 minutes, and I will try to capture a proof of this fact. And so maybe from this argument, you have seen that if we have a graph with maximum cut rank k, then we can always find an AB cut in G with the full rank, with the full rank, and they have the same size, which is k. And so if I let H be, then we only have to care about the average cut rank of H. So actually, what we really need to show is that the average cut rank of H is at least k over 4. And so now the problem boils down to prove this inequality instead of to prove the inequality for G. And we know that the maximum cut rank of H is still is still k. Okay. And so now we can let S be a random subset of VH, and then A cap S and B minus S are random subsets of A and B. So let me draw a picture here. And one thing you can see is that the cut rank of S in H is at least the rank of the A cap S and B minus S cut, right? And so I guess it's inequality. So because of this inequality, we will have to show that the expression with respect to y of the xy of the rank of the xy cut in H is at least x over 2 for every fixed x and x set of A. Because if this is true, then we get the desired result. Okay, because the expectation of x of the size of x is a over 2, which is k over 4, and so it is enough to show this inequality. And we use the same trick here. So let's say now we have another picture. So now we have A and B. Right, and because the rank of the AB cut is exactly k, there must be some in here's x. There must be some z here, satisfying that the rank of the xz cut in H is exactly the size of x. That is still matrix algebra, right? And if y is a random subset of B, then y cap z is a random subset of Z. So we have this and this y. And so because of that, we come to the conclusion. So we just replace y by y cap z inside the term, and then we take the average again. And that concludes the proof. Okay. And any question?
Is there an example that decoded
Maybe no. I'm not so sure about that, but I mean there are a lot of examples where this inequality fails. But to keep this constant term for, then I'm not so sure. Maybe.
So it can be reduced.
Yes, somehow. I guess that. I haven't tried, but I guess this.
Anyway.
Also a question from audio.
Yes.
Do you know whether the factor 4 is tight in the max cut rank is at least 4 times average cut rank?
Sorry.
The factor 4 in so max cut rank is less or equal than 4
Just
times.
uniform. Yes.
This is
So
the tightest.
so I guess it is not tight.
It's probably not tight.
Not tight. But I know that there are a lot of examples where the maximum cut rank is very close to the average cut rank. There are a lot of examples where they are very close to each other and actually close to half of the size of the graph. A lot of examples. But this constant term for, I'm not so sure. And I guess maybe there is another way to prove this inequality and replace this bound 4, this factor 4 by maybe 2 or even 1 point something. But it's just my guess. I'm not so sure about it. Okay, thank you. Okay, so I have 5 more minutes. And for the last, I will present the results saying that these results actually characterize all graphs of average cut rank almost 3 over 2. And the number 3 over 2 is a bit unnatural here. We chose this number just because we couldn't do for 2. And so we could only do it for 3 over 2. But still, so if G has no isolated vertices, then the average cut rank of G is almost 3 over 2, if and only if G is a vertex-minor of these graphs, of one of those graphs. And here EK is the star on K plus 2 vertices with 1S subdivided. And we can characterize the set of all possible values for the average cut rank of graphs in this interval, which are only this kind of discrete set. This kind of discrete. And there is actually a result says that given an alpha non-negative, then there is some there is some delta alpha such that every graph has average cut rank outside this interval, this open interval. So it somehow justifies the discrete property of the set here. And so in particular, the set of all possible average cut rank is not dense in any interval. So, so you can say that the average cut rank is not that far from being integral, like maximum cut rank and rank width and linear rank width. Okay, so this ends my presentation. Thank you. Any question?
Yeah, you said what I would say. Any questions?
So you said that there are many examples where the average cut rank is close to the maximum cut rank?
Yes.
Are they dense graphs or sparse graphs, or like the size of the graph is close to linear in K? And do you have
The size of the graph is roughly n squared over 4. Actually, there are two ways to do that. The first way is to consider the random graph.
Size is number of edges for him, or
okay.
I don't know.
So when you say n squared over 4, is it what is n there?
N
the number of edges is n squared over 4.
N is the size of the graph, it's the number of vertices,
Okay.
and n squared over 4 is the number of edges.
Okay.
Okay, so I consider this model. And actually, you can consider an alternative model where you add the vertices one by one. So you start with just one vertex, and then instead n, you add one vertex and the edge, and the probability that there is an edge between a new vertex, the new vertex, and an old vertex is 1/2. And so somehow you will get into the fact that there is a graph G on n vertices, and here the n is very large, such that the average cut rank G is at least n over 2 minus 5c, maybe something like 3 here, minus 2 over pi, and the square bracket. And it is close to the best possible, because if if the cut rank of every set is the maximum possible, so that's if the cut rank of S is exactly the size of S for every S in VG and S at most n over 2, then you would have that the average cut rank of G is roughly n over 2 minus maybe something by doing approximation as far as I remember.
So have you looked at expander, like sparse, like cubic expander, for example?
Yes, I tried, but I didn't get past this bound. I couldn't get better. So maybe, I'm not so sure, but this was the best that I could find. But this result does not an implication of this result, because if you consider this model, then you can only get graph G with average cut rank at least n over 2 minus n log n. And for me, this is the best possible.
And when?
No, maybe square root of n log n. And this is the best possible if you consider this random graph model. But if you add the vertices one by one, then you can show that there is a graph G. So just by considering a different model, you get a different graph with this property. It's a bit weird, but I've found this kind of vertex random graph model in a paper by Alon. In his paper, asymptotically optimal induced universal graph, and he introduced this model as a replacement for the traditional arbitrary random graph. And he used that, as far as I remember, to prove that there is a graph containing every graph on n vertices as an induced graph, and the size of that graph is not too big compared to the previous result. So that's just my finding, and I will be really happy if someone can replace this bound. But yes, so C here is some constant. C here is some constant, and if you don't, and if you want to get rid of this C, then you can just say this 2 here, because 2 is 6 and 3. Okay.
Other questions? Yeah, with that, let's thank the speaker again.